All right, welcome to this webinar on CLT design using FEM-Design. My name is Isaac and I work with business development here at Matrix Strusoft. So we have this collaboration between Matrix Software and Strusoft where we have a package deal containing the well-known for you Matrix software such as tools and Matrix Frame and so on, together packaged with FEM-Design, which is a full finite element software for analysis and design in 3D with multiple types of materials, such as, for example, concrete, steel, timber, CLT, foundation, masonry, and so on. And in this webinar, I will go through the CLT features when it comes to analysis and design in FEM-Design. Again, if you're interested in this package deal, you can just reach out to one of our sales representatives in Netherlands and they will help you out with a demo and also help you get started basically. Also during this webinar, if you have any questions or any issues with the sound or anything like that, please feel free to provide your question and your comment in the question button in the GoToWebinar interface. You will normally find it on your right-hand side, and there you can provide your question, and I will try to go through all the questions at the end of the webinar. Okay, so here you can see the agenda for today. We will start with a short introduction of the software FEM-Design, go through some of the theory of the CLT and how to model, how to view result design, and then at the end, some documentation. We also have a free trial for FEM-Design. You can try it out for basically in a specific project you need, or just try it out for fun. And together with that, we also provide like a custom-made demo for you, tailored to your specific projects. But let's jump into the presentation and begin. So just a very short introduction of myself. So I've been working at Strusoft for about 8 years, and before that I worked as a structural engineer within the industry sector, mainly with steel and concrete, for 5 years. But since joining Strusoft, I also worked quite a lot with the CLT module, which is the topic for now. And FEM-Design, this is our main 3D analysis and design software, finite element software. It's a modular software. That means that it's divided into different modules and you can put together a package that fits your specific needs, and then you get a very like a nice setup that's tailor-made for you basically. And in this deal we have together with Matrix Frame and Matrix Tools, we have FEM-Design basic package, and that can include, for example, timber design, CLT design, or steel and concrete, or however you might combine 2 different design modules, but it's up to you to decide. So in this specific demo, in this webinar, I will be using 3D structure, which is the main modeling and analysis module for FEM-Design, and timber design and CLT design, which is 2 different design modules, one for general timber and one specifically for CLT design. So when it comes to CLT design, there's a couple of different aspects that you should consider. And let's just jump into the theory, and hopefully those different aspects will be a little bit clear for you moving forward. All right, so first of all, since a CLT is a laminated shell, you have multiple layers in different directions on top of each other. They have this specific behavior compared to homogeneous shell or homogeneous plate. And that's mainly this coupling effect between axial force and bending. And that is described using the coupling part in the stiffness matrix. And that can be seen here. And one of the theories that addresses this is the laminated shell theory. And this is implemented in FEM-Design, which will give you a correct behavior of the CLT. compared to just doing with a homogeneous normal plate or wall. So normally we have this D matrix, which is the yeah, this. Okay, so here we have different results that we're looking for, and here we have the stiffness, and then we have different deflections basically, or displacements here at the end. So normally this middle matrix here is the stiffness matrix, and this D part usually it handles bending and so on. A part is more related to membrane action, and the S part is the shear. And normally the other parts of the stiffness matrix is 0, but that's not the case using the laminated shell theory. Here we have a part called the B over here and also over here, which is a coupling between axial force and bending. And this means that you will get a different behavior compared to using a normal homogeneous shell theory. And let me just demonstrate that real quick what I mean. So I will jump into the software and show you just a quick live demo before continuing with the theory. So here we are inside of FEM-Design. FEM-Design, you have a main 3D view in the middle. You can rotate this by holding down Control and the middle mouse wheel, and you have some different tab structures on top here. In general, when working with FEM-Design, you are working from left to right, very similar to Matrix Frame and Matrix Tools. Then if you're sticking to that way of modeling, you will get a natural and good modeling flow working through your project. And if you open up a specific tool, let's say we open up the timber plate tool, you will get a pop-up, and here we have two different modes of operations: either draw new objects with the pen or change properties of existing objects using the question mark. Then we have some other object-specific tools following that, but I will select the properties and just view the properties of these two shells that I've modeled in the 3D view over here. So let's take a look at the properties here. And here I have created a specific CLT, and it looks like this. We have different layers, and it's actually asymmetric. So we have in the bottom, we have two different layers that's in the same direction. And this is done to have this eccentricity in the CLT to highlight this kind of behavior that I just talked about, the connection between the axial force and bending forces in the shell. And if we click on the display stiffness here, you can see that we have the flexural stiffness matrix, that's the D part that I just talked about. We have the membrane stiffness parts, that's the A part, and the shear stiffness matrix part, which is the S part in the previous picture that I showed. But we also have this eccentricity or coupling stiffness matrix, which connect the flexural stiffness and membrane action. And this is not 0 since this is an asymmetric CLT, and this will give you this kind of behavior. So to highlight this, I have this CLT first oriented in this direction and then oriented in the perpendicular direction. This indicated by the arrow inside this plane of the CLT to indicate the main direction of the CLT. And I've also applied an in-plane force. It's just a line load in plane on both shells. So if I now take a look at the results and look at the displacements, and let me just increase them a bit so we can see it more clearly, maybe 20 here. All right. So when loaded in plane, I have a very small flexural stiffness, bending deflection here. It's mainly just the connection between the main and perpendicular direction here that gives some forces in the, in this case, local y direction, which gives some bending. But the majority of the bending comes in the other direction because that's where it's asymmetric. And here I can see, even though I only loaded it axially in plane, I also get a bending in this, so it will actually bend downwards. And this is the behavior that is modeled using the laminated shell theory, and an important aspect when working with CLT, because it's not behaving as a homogeneous plate. Another aspect of the CLT is that you will get results in between each layer of the CLT, which can be used for design and so on. But I will come to that soon later on in the presentation. But this is an important aspect, and just to get the correct behavior in the finite element model, basically. Let's jump over to the theory PowerPoint again, and let's take a look at the reduction factors. Before, when we define CLT, a CLT plate, you often have these kind of reduction factors, which commonly comes from the manufacturer or some literature. And here you can see R33, for example, R66, 77, and 88. And that is a reduction factor that's inserted into the stiffness matrix in that specific position. So R33 means basically column 3, row 3. That's this position in the stiffness matrix. And these different reduction factors can be adjusted as you would like inside the software, either when using an existing CLT in the library or defining a new CLT from scratch from a specific manufacturer, or maybe doing something very specific. When it comes to the Eurocode checks, there are some limitations in the current Eurocode. I know there will be more of the CLT checks implemented in the Generation 2 Eurocode. And we're on top of this actually already started the implementation of the Generation 2 Eurocodes. So rest assured you will be updated, and the software will be able to handle that, of course. But in the Eurocode today, we have tension and bending that's described in Eurocode, compression and bending, and shear checks. However, there are some additional checks implemented in the software based partly on the Generation 2 Eurocode, but also other literature, basically the industry standard of checking CLT, which is the shear interaction, tension and shear, and compression and shear. However, in FEM-Design, we also have two other things, which is kind of unique, I would say. It's, at least we were very early to implement this. This is, first thing is the buckling of CLT. And this will calculate a corresponding area in a arbitrary direction. So it could be in either direction, basically, or a slanted direction. I will show that later on in the software, and calculate the buckling for this part of the CLT. Also fire checks, which will take into consideration the shoring of the CLT plate and perform the checks that's necessary for the fire. Basically also checking delamination and checking the reduced section for the applied loads. All right. I will very soon go into how to define a CLT, but before I do that, I would like to explain two different settings that's also available in the software. The first one is the glue at narrow sides, and that's described in this top picture over here, which if you look very closely, you can see some blue lines between each plank in a plane of the CLT. And that's basically if you decide to glue at the edges of the plank together when you manufacture the CLT. This is typically done by some manufacturers, but maybe not for other manufacturers. And that depends. It can also be product specific. So it's something that you should keep track of. If you apply glue at narrow side, the torsion check will not be carried out. But if you do not have glue at narrow side, there will be an additional torsional check for the CLT plate to check that you have enough adhesive on the bottom of the planks to handle this torsion effect. The other setting that's important to take into consideration, it's the shear coupling between the different layers. And this is normally always the case that this should be on. That's indicated in the bottom picture here. You can see some green highlights here in between each layer. That's basically if you have glued together different layers. Otherwise, there will be no interaction between each layer. And typically when you're doing a CLT, it's always glue between the layers. But in some specific cases, maybe if you're doing an accidental check, or maybe if you have a damaged CLT building or something like that, it can be an idea to check without any shear coupling. Then each plank layer in the CLT will act individually, and there will be no shear transfer between the different layers in the CLT. So those are two options available in FEM-Design when you define a CLT. All right, so let me just show you that real quick in this model, and so you can fully understand what I mean. So the first option here, it's the glue at narrow side or not. And here we have an option where you don't have any glue at narrow side. And if I go into the code check for this CLT, I will show you more step by step later on in the presentation, but now I'll just show you this real quick. And yeah, so here we have the code check, and here we have an additional check when you don't have glue at narrow sides of torsion. So this is checked if you do not have glue at the sides. However, in the case where you have glue at sides, which is this right plate over here, if I check the code check for this one, I will see that the torsion is basically just set to not relevant because this check is not carried out in this case then. When it comes to this shear coupling on or off, I'll just very shortly highlight the difference inside the results. So let's take a look at the shell laminated shell stresses. That's basically the stress over the cross section for the CLT. And we can take a look at a specific point here. If we take a look at the detailed settings, and I will select a result point, which I've already created here, which is it's in the same position for both plates, and it's the same loading, the same section. The only difference is that in this plate I have shear coupling on, and on this I have it off. So if we take a look at the shear coupling on, I can see, for example, the sigma X component that I have shear transfer between the different layers, which means that I have a linear distribution of the stress over the entire cross section here, which is like normally always the case. However, you have the option to turn this off and have each individual layer act individually, and then the distribution of the force will look instead like this. So here you have each layer linearly, but it's reset between each layer, if that makes sense, if you understand what I mean. So here you have from a linear from positive to negative within this layer, going to the next layer, it's the same. So each layer is working individually. That could be an option and a good idea to check in some specific certain situations where you don't have this, where you lost this interaction between the layers for some reason. But it could also be that you're doing a check for a general laminated composite. So this laminated shell theory, it's not only for CLT, it can be used for any laminate structure. And in that case, in some cases, you don't have this shear coupling, and that setting can also be an important aspect in that case. So let's continue with the modeling, and I'll highlight some key features here. So I'll show the existing library and how you can select different plates from that. I will show you how to create your own CLT and also show this general laminated composite, which is basically a way of creating a laminate with any arbitrary material, any arbitrary thickness. So let's jump over to FEM-Design again. Now let's go to the structure tab, which is the tab where I create and model my structure. So I will open up the tool called Timber Plate, and this tool I will create some new CLT plates here. I will select the pen to define a new plate, and I click on the default settings button to select the settings for this plate that I'm about to define. So if I click here, it will open up the material library. So first, on the first tab, I have some settings, some different eccentricity settings and so on. I won't go into too much detail here. Instead, I will focus on the material tab. And here I have a mechanical model to select. Either the orthotropic shell, which is this homogeneous material model, or finite element type, which do not have this coupling effect. But if I here instead select the Cross Laminated Timber, now I will use the laminated shell theory, have this coupling effect, have the more advanced finite element type, and so on. So here I can see the different manufacturers that we have in the library. But if you're, and if I go into for example, one example here, I can click on modify and I can see the properties of this. So if I can highlight certain layers and I can look at the properties for each layer basically over here. They are divided into mechanical properties, but also limit stresses. So the mechanical properties are typically stiffnesses, new values, and so on. And the limit stresses, well, it's the limit stresses for each layer, which you can set individually. If you want to create a new CLT, you can click on New over here. And if I have selected a specific CLT, I will have this as a baseline. I will start out with this one. So now I'm starting out with this Binderholz 125, 150, and I can create a new one and I can change, for example, let's move over to the mechanical properties. I can change the thickness, and you can see in the viewport here that the thickness is updated. I can also highlight a specific layer and it will highlight in the table here. I can also add additional layers, and if I double click here, I will get the timber material library, and I can select a timber material and it will give me the default values for this timber material, but of course I can change this if I want as well. Also, it's actually possible in FEM-Design to have a slanted angle. Normally this doesn't really exist today in the current industry, but you could set an arbitrary angle of each layer, because this is a general tool which could be used for general laminated composites, and therefore you have this ability to set an arbitrary angle, but normally it's always 0 or 90 degrees. All right. Also important to know that we have some settings over here. So we have the KDEF value, dependent on the service class, and this is the default value that's shown by the software when you select a specific panel. You can set it here, but you can also, of course, change that later on when you're modeling, when you're selected. Also here we have the stiffness reduction factors, which I just talked about. You have the drilling R33, that's referring to column 3, row 3 in the stiffness matrix, and so on. And these are normally adjusted according to literature or according to the manufacturer's product table. So something to keep track of here as well. All right. So here, when I select a service class, I will have these different default KDEF values pre-selected for me, but I can, of course, select them myself and overwrite this if I want to, and I do that in these this area over here. So we've actually divided up the creep value, the KDEF value, to have individual creep values for quasi-permanent SLS, frequent SLS, and characteristic SLS, also for the ULS. This is a great tool because you can have different creep behaviors in different loading situations, basically. Typically, you want the creep value to be 0 in the characteristic because it's the instantaneous deflection. But here you have the possibility to actually change this manually and really fine-tune the behavior of the deflections. And of course, deflections is a very important aspect when dealing with timber structures in general. And here we have these two options that I just talked about, the consider shear coupling between layers and the no glue at narrow sides. So here you will find these different settings. So when I have selected a plate, a CLT plate that I want, I just click OK and I can draw it. And I start out by drawing the main direction of the CLT, and then I can define the CLT like this. And I can show the thickness here just to highlight the thickness of the plate. All right, so if I would like to continue working with a general laminate composite, which is not CLT, just mix any material. It could be like, for example, a sandwich structure. It's quite common that you have sandwich walls and so on. It could be like some kind of steel sheet, some insulation, and another steel sheet, or basically any combination of any material in a sandwich structure. You will go into the mechanical model and change it to general laminated composites. And here you can create your own material and your own behavior basically from scratch. All right, so again, this is a general method. It can be used for any general composite. All right, so that's the modeling part, how you can create your own CLT and choose from the existing library and some key aspects. If you're interested in learning to actually model in FEM-Design from scratch, we do have a lot of resources to get you started with that. In this webinar, I don't really have time to go in too much detail when it comes to that. Instead, I will just focus on the important aspects for the CLT. Let's continue to the results. And here I just want to highlight two different things. It's really important when dealing with CLT to keep track of the different coordinate systems, because you have a global coordinate system in the model. You also have local coordinate system for the plate object, but you also have local coordinate system for each individual layer. So it's important to know which coordinate system you're viewing and yeah, to have to view the result in a correct way, basically. Also, there are some settings to find different max and min values, which I will show you. So let's jump over to another model, which is a little bit more realistic maybe. And let's take a look at the results. So in this model, I actually have a hybrid structure. So it's a concrete core and a concrete slab. And on top of that, I have some timber columns and beams and some CLT. I also have some steel also in the bottom part here. And I've used the 3D soil module, in this case, the foundation design module, to calculate the bedding modulus underneath the structure automatically from the soil properties, which is another nice feature in FEM-Design. And that's why it's showing the bedding modulus result here. So if I take a look at the compression result, I will see the calculated value for the bedding modulus underneath this structure. But in this webinar, we're focusing on the CLT, so I'll continue with that. Here we have the results, and it's divided into load cases and load combination and maximum of load combination. If we take a look here, we have displacements in the model, we have reactions, we have different connection forces, stability checks, where you basically check that the resultant is inside of the, yeah, you're basically checking for overturning. Bar internal forces, that's like normal forces, moment, shear forces in bars, columns and beams. Bar stresses, shell internal forces, that's moments in each shell. And we have also shell stresses and laminated shell stresses. I'm going to focus on the laminated shell stresses because this will show you the stress in the CLT, the laminated shell, and in different layers. So let's take a look to expand that result. And here I have different stress components that I can view. So I have the sigma x at the top, sigma center, sigma x bottom, but let's take a look at the von Mises, for example, at the top. Then I can select my load combination and the layer that I want to show. So in this case, we have 5 different layers in these CLTs, and I can show a specific layer and display this as a graph. And I can view this stress component for this specific layer for the entire model. Here I can also select if I want to view it in the shell local system, that's the plate, or the layer local system, that's each individual layer. So it's like the X direction will be first in this direction, then it's 90 degrees in the other direction, and so on and so forth. So that's important to keep track of when dealing with these results. If I want to take a look at this kind of stress distribution over the cross section, I'll just select one of the shell stresses results, and I can go into the magnifying glass detail results, and I can select a plate and select a point on this plate, and it will show you the stress distribution in this specific point. So here I see the specific shell. I can see the stress distribution for this stress component and the other stress components as well. And typically what you want to do is to find the maximum stress in a specific region. And then you can go into the result called maximum of load combinations. I will select the laminate shell stresses and select the stress component, this one for example. And now when I go to the detailed results, I have the option to select laminated shell, and this will automatically find the max and min positions for each stress component. So if I take a look here, I have different positions. So PT1, that's the maximum stress for the sigma X stress component. PT2 is the sigma Y, and so on and so forth. So you can see here that this stress distribution is valid for in this specific point. Here we have another point, and so on and so forth. And now I'm looking at the all components positive. I can also look at all components negative to find different points and to find the maximum negative value, over here at the top, maximum negative value for all components and these corresponding points. So if I switch here, you can see that the different points will switch position basically. And this is a great tool to just find out the maximum values in between different layers and so on when doing when we're viewing different results. All right, let's hide this result and let's continue. So now I will move into the design part of the CLT. Again, if you have any questions, feel free to provide them in the GoToWebinar interface, and I'll get to them at the end of this webinar in about 15 minutes. All right, so let's continue with the design. And here I want to highlight some specific things that's important. This is not, of course, this is not the only checks that's carried out. I showed previously that we do check all the checks according to Eurocode with additional checks according to Gen 2 Eurocode and some additional literature, but just to highlight some important aspects. So we have the buckling check, fire design, and deflection checks and eigenfrequency calculations. So let's start out with a normal ULS check, including buckling check. So if I go to the timber design tab, I can select the design mode over here. So I have options to design timber bars, orthotropic panels, that's homogeneous panels, CLT panel, timber bar fire design, and CLT panel fire design. So that's the different design options that's available under the timber design, basically. So now I just want to do a normal ULS check, and I'll go to the CLT panel. Here I have some settings. If I go to the calculation parameters, and they are object specific, so you can have different settings for different objects. So when I select this, I need to select a specific object and change the properties, the design settings for this specific object. So here, for example, I have the option to either carry out or disregard the shear interaction formulas and the torsional checks. Since these are not covered in the Eurocode, we have put these checking options as optional because sometimes you might, for some reason, don't want to carry this out because you only want to fulfill Eurocode. These are additional checks outside of Eurocode. Then you have the option to not do them basically if you don't want. But we recommend to actually do them because they're supported in CLT literature in general. And then we have some buckling settings. So here we have a reduction factor for material properties when doing the buckling check, as well as a beta C value. This is not the buckling length. This is instead another another factor in the buckling check. We'll take a look at that real soon when we check the formulas. So when I'm happy with this, I can just carry out the check, and I can just right click on an object and carry out the check for this object. If I want to view step-by-step calculations, I can go into the CLT panel utilization result, double click here, and I'll click on the magnifying glass and select a specific panel. And this will give me step-by-step calculations for this panel. So here I can see the tension and bending, references to Eurocode, compression and bending, reference to Eurocode, and so on. And here we don't really have for the shear interaction, tension and shear, and so on. We don't have a reference to Eurocode because this is the checks outside of Eurocode. So if you want a reference for these, you need to go into the theory manual for the CLT, and then you can find all the referenced material there to carry out the check. So now you can see buckling not relevant. That's because I haven't defined a buckling length. So since this is a plate and it doesn't really have too much normal force, it's maybe not relevant. So instead, let's take a look at the wall over here. So let's say that I want to check this part for buckling. It's an opening here, maybe a window, and on the other side it's also a window. So I have a smaller segment here of CLT, and I want to check this for buckling. So now I go into the buckling length setting over here. I can define an area, and here I can set any arbitrary direction. So it can either align with local X, local Y, or any arbitrary user-defined direction. In this case, it's actually aligned with the local X direction because it's in this horizontal direction. So let's just right-click on this element and draw this area, and I can set a buckling length, let's say maybe 0.8, something like that. So it's hinged at the bottom, but it's fixed at the top. So you can also get some help here if you would like. So 0.7 maybe, but maybe it's not that fixed because it's CLT. So yeah, you get to set your beta factor however you would like to here. These are just based on the Euler cases, and they are idealizations. So we recommend you can use these as a help, but you should of course think closely about the different beta factors that you insert. All right, so let's just for fun, I can draw an arbitrary direction here. This could be a good idea for a shear wall, for example. When you have a shear wall, it could be compressed in a perpendicular direction, or sorry, in a slanted direction across the panel if it's a shear wall. Then I can actually select a user-defined direction, and I can draw any arbitrary direction and define the buckling in that specific direction, like this. I can also draw an area that aligns with this direction as well. But let's carry out the buckling check for this area. I'll carry out the check and I'll take a look at the result again. And now I can see the buckling part at the end here. So here I see the calculation for the buckling, and here I see the beta C value that's used in the buckling check, and that's not to calculate the buckling length. That's instead done here by multiplying the beta factor that I set to 0.8 with the length of this area that I defined. And I get a result. In this case, it's actually buckling a little bit. So yeah, it's a nice way of checking these kind of areas where you have maybe a smaller part of the CLT and you're afraid of this buckling for a wall or something like that. Let's continue with the fire design. And the fire design is, to carry out the fire design, you have to define a load case. You do that on the load tab. You go into this button called load cases. And here we have a fire load case with the type set to +fire. And this load case it's just an empty load case, but this is used as a marker to select which load combination should be used for the fire design. And there could be other accidental load combinations, for example, seismic or any impact loading or something like that. So it could be multiple types of accidental load combinations. And by including this fire load case in the accidental load combination, the software knows that this load combination is used for the fire design. So if I take a look at the bottom here, I have an accidental fire load combination defined with the type set to ultimate accidental limit state, and here I have included this empty load case with the plus fire. So that's how the logic works and how to distinguish between different accidental load combinations. So let's jump over again to the timber design tab and go to the design selector, and instead of designing a CLT panel for ULS, I'll go to the CLT panel fire design. And here I'll find again object specific settings for the fire design, and I'll reach them by going to the calculation parameters, and I can just select a plate, and I can select a duration of the fire, let's say 20 minutes, and a bunch of other settings here. So first off, here we have the charring rate. And if you click on calculate automatically, it will be taken from the Eurocode table, which describes the charring rate for different types of timber materials, basically. But you can, of course, set this to any other value that you would like. Then you have this delamination effect, which is basically the glue between the different layers failing before the actual charring rate has reached this point. And this is normally handled by a charring rate multiplier. And this could be set here. So you're multiplying the charring rate to take into consideration this delamination effect. That's described in literature as well as in the theory manual for the FEM-Design fire design. So you can read more about it there. But that's normally how you deal with this kind of delamination effect, which is an important effect. Also, for all fire design calculations in FEM-Design, we have a buckling length multiplier. For those area when you have buckling checks, you can have a buckling length multiplier to increase the buckling length with this factor for the accidental load case. We also have some reduced section options here. So first of all, you have this applied standard value D0, or you can use the standard value for the D0, or you can select your own. But there is also another important setting here. It's the neglect shard layer thinner than a certain amount. So the sharding won't be completely even over the entire cross section. It won't be like even all the way through. Instead, it will have some areas where it's a little bit more, a little bit less, and so on. And if you have a sharding which just leaves one small part of one layer, plank layer in the CLT, if you take into consideration that very thin layer, you actually could sometimes be on the unsafe side. So this setting will disregard layers thinner than a certain amount to take into consideration this uncertainties of uneven charring rates in different areas. And also this, it could give you too much beneficial, like basically results on the unsafe side if you do not consider this in some cases. So we do recommend to take a close look at this, read the literature, and insert the value that you find is applicable for your specific project. To neglect if it's a remaining part of the shard layer thinner than a certain amount. So in this case, if I set 5 millimeters, for example, if I have a sharding rate that's reached just 4 millimeter thin remaining top layer, for example, this entire layer would just be disregarded. Okay. Then we have this protection by connected structures. And this is if you have a connected structure that will delay the charring start time. And if you have inserted a protection by connected structure, you won't have this flash fire effect when you start the charring rate in the CLT. But if you apply some kind of insulation or fire protection, for example, gypsum, and that fails after a certain amount of time, you will have a flash fire effect, which is basically increasing the charring rate for a certain amount of time because of this flash fire effect. But that will not be considered when you're using this connected structure setting. You can also select which sides of the CLT is exposed to the fire and not. All right, so let's just run a quick check here, and we can see we have actually managed to carry this without any protection. So we can take a look at the CLT panel utilization and just go to the magnifying glass again to see the results. So here we can see the reduced panel size. So we have a sharding of 20 millimeters, and then the normal checks, they are carried out for this ULS load case or load cases if there are multiple, with this reduced panel size basically. If I want, I can actually also add protection. So let's just add that. I do that with the pen here, or I can also do it automatically, but just to keep it simple, I'll do it manually. Here I can add, for example, different wood or gypsum or rock fiber or something like that. Let's just add some gypsum board here, like that. And this will actually delay the sharding rate start time with a certain amount. And if I now take a look at the result again, we have a smaller shard. It was just actually 1 millimeter in this case, but still. It's a little bit smaller because I have this protection after a certain amount of time, and I have this slash protection of the seal. Hopefully you can hear me still. If you're experiencing any issues, just write in the chat, and yeah. So I'm just wrapping things up here. I'll just show you a few more things, maybe 5 minutes, and then I'll go to the questions. All right. So that's the fire design. And let's take a look at the next option here. Let me just real quick take a look at the chat and see if everything is okay. Everything seems to be in order. The next thing that I want to highlight is that this is a full finite element software. So you have the option to run multiple types of analysis. So for example, you can run eigenfrequency, seismic analysis, footfall analysis, which is a great tool to calculate accelerations and so on in a CLT plate. You have some time history options, periodic excitations, you can do a stability analysis, and so on and so forth, construction stages, and so on. So you have, and all of these are of course compatible with the CLT. So you can do CLT calculations with all these different analysis options. In this case, I've actually run an eigenfrequency calculation just to show you this. And let's take a quick look at the results. So let's go to the eigenfrequencies here, dynamic analysis eigenfrequency, and I can take a look at the vibrational shapes for this structure. So here I have the eigenfrequency for this, and it's about 5.4. And yeah, I can also animate the mode to understand how it looks basically. And there's also something called story fundamental frequency, and that's calculating the eigenfrequency for each story in the building. And that's also a very nice thing because it follows the Eurocode quite nicely, where it says that you need to check the eigenfrequency for each story basically, and that could also be carried out in the software. In this case, this structure is not really a typical story by story structure, so I haven't defined any stories, but I could possibly define a story here and a bottom story and do an eigenfrequency calculation for each individual story. Another important SLS check is the deflection check, and that will be found under the analysis tab. And if I go to the deflection option over here, I can set which load combination should be checked for deflection, and I can check multiple ones. For example, I can check the long-term quasi-permanent and the short-term characteristic. And I can check this both for bar elements like beams and columns, but also for shell. So let's actually check the shells here. Let's just hide this result real quick and take a look at the shell. So here I have different criteria that I can set up for this specific element. So I want to check the deflection, for example. I want the L value to be like either the shortest edge, in this case 6 meters, the longest edge, it's 6.7 meters, or a user-defined value. And then I can set different criteria depending on the different SLS load combinations. So for the long term, for example, I might have one deflection criteria, a relative limit, or an absolute limit. And for the instantaneous deflection, I might have another result, another limit that I need to consider. And I can set them individually and check them individually. And this deflection check will, of course, be relative deflections. So if if I have, let's just run the check real quick here. If I have a global deflection which is big, the relative deflection will take into consideration and subtract the deflection at the edges, basically. So in this case, I have calculated the bedding modulus, and the deflection in the bottom bedding module is quite large. So if I take a look at the global deflection, I have some global deflection at the bottom here, which will influence, of course, this deflection over here. So if I take a look at the specific value in the middle here, it's actually also including that the entire house has like sinked down a couple of millimeters. But if I'm doing the deflection check, it's the relative displacement. So it will check at the border of this specific element and subtract the deflection at the border to just check the deflection for that individual object, which is what you want, of course, for a deflection check. You are not looking at the global deflections when you're doing a deflection check. You're looking at each individual object, taking into consideration the deflection for that specific object. And that's exactly what I'm getting when I do the deflection check. So I will have a result when I've done the deflection, which can be found here on and I can take a look at the utilization for deflection example. So here I don't actually fulfill my criteria. I have actually much more deflection, so 227% overutilization. And I can see the value here, which is the relative deflection. So you could see before that I had the total deflection of about 116 or something like that. Now it's actually 45 millimeters, which is the actual deflection of this, subtracting the deflection of the global influence, if that makes sense. All right, so I think that's it for this presentation. Could I take one more minute of your time just to show you the documentation? So there are, as you've seen, we have the step-by-step calculations to show and highlight the design checks for each each CLT, actually each design software, regardless if it's concrete, steel, timber, CLT. So you can do the documentation either inside FEM-Design or outside FEM-Design. So if you're doing it outside FEM-Design, you're typically looking at some raw, and then you can select, you can list, for example, having some issues here with my audio. I'll just turn off my webcam just to get some extra bandwidth so that the audio is clear for you. All right. And this is then to clipboard, and I can paste this into, for example, Excel or any other software that I use and get the raw data from the software to Excel. Let me just open up Excel real quick here and I'll show you that. I'll just paste it here, and here I have the max and min internal forces for these load combinations for this plate in raw data, which is really nice if you would like to do the documentation outside of the finite element software. Otherwise, we have a full documentation module, which you can create your documentation and have a dynamic documentation inside the software. And let me just buy a template here, and we can take a look at just a basic layout, how it could look. So you get different types of results on this left-hand side over here, and it will show you how it looks in the view in the middle over here. And you can add and change different results, like arrange them in different ways and so on. So it's, yeah, you can just drag and drop, hide different columns, that kind of thing, just to adjust and change the documentation. And we actually put quite a lot of effort into this documentation module the last couple of years. So now it's quite interactive, it's quite easy to use actually. And you can of course export this and print this as a PDF, or if you would like to export it to Word or something like that, that's also possible. All right, I hope you can hear me still, and that actually wraps up this presentation. If you're curious to try out this yourself, you can apply for a free trial at strusoft.com, or you can just reach out to your sales representative at Matrix Software or me myself, and I'll try to help you out. Thank you so much for attending, and also all the examples and the presentation will be sent out in a follow-up email to you, so you will get all that information as well. Thank you so much for attending this webinar. Now I will go into the questions. So if you would like to hang around to hear the answers to any remaining questions, please feel free. Otherwise, thank you and hope to see you in the next webinar. All right. Let's take a look at the questions. Okay, I have one question over here. So it says, is there anything known or required to calculate for deformation and stresses in the material due to changes in humidity in the panels? So this is, there is no more advanced model compared to the one presented in the Eurocode, which is basically the creep value. So the creep value will take into consideration the humidity and also the material type and so on. So that's actually taken, like setting the KDEF value is taken into consideration the humidity, but it's not, there is no more refined way of doing it than inserting a KDEF value. All right, hope that was an answer to your question. Let's see here if we have any other questions. Yes, about this package deal. So yeah, we have a package deal for this FEM-Design. So we have this collaboration between Matrix Software and Strusoft, and we have a great package deal, which is actually good both Matrix frame tools and FEM-Design. And you, if you select to go with this, you will also get our representatives. Question here, let's see. Is it possible to check CLT point-shaped any type of geometry, any type of loading, any type of support conditions? So let's jump over to the software real quick here. So here I just draw this plate, CLT plate, and here I have, for example, the support. So I have point supports, I can place them in any arbitrary position. I have line supports, I can place them in also any arbitrary shape or position. I have also surface supports, which also could be placed anywhere basically. So, and The different supports have ideal elastoplastic behavior, which means that they have okay, so this K set is the stiffness in the Z direction. So you have the possibility to set one stiffness in compression, another stiffness in tension. You can also set a plastic limit both in compression and in tension. So it's like a non-linear support where you can set a stiffness in compression and tension, and also with a plastic limit, also different in compression and tension. So yeah, so in general, it's like a general finite element software. You can create arbitrary geometry, arbitrary loading, arbitrary support conditions. So I hope that was answer to your question. All right, so let's see if there's any more questions. It seems like that was it. If something comes up, feel free to contact me. I'll be happy to help you out in any way I can. And again, thank you so much for sticking around for the Q&A part of this webinar. That concludes this webinar. I will close it down. But again, thank you for attending. Have a nice day. Cheers. Bye-bye.